This is an atom, as scientists simplify it for us. So incredibly small, we will never see one. Yet the atom is mainly empty space, with electrons whirling around the nucleus. But man succeeded in smashing the tiny subatomic nucleus, releasing enormous and unprecedented amounts of energy. War and peace were revolutionized at the dawn of the atomic age. Our solar system in the universe around us, also mainly empty space, so vast it staggers human comprehension. Still, man is now conquering this vastness. Strange devices float in the emptiness between our Earth and the planets. Men walk in space. Science fiction becomes science fact. As more ambitious space feats take shape on the drawing boards, one need becomes imperative: more power. So, the experts of space rendezvoused with the masters of the subatomic world. For only the atom can satisfy some of the future power needs for space exploration. One has to use the tiniest fragments in nature to reach into the vastness of the universe. Nuclear energy is being developed for our space program in two basic applications. First, for nuclear space propulsion, the nuclear rocket. Secondly, in special power plants, which can provide the electricity essential for every spacecraft, where solar energy is unsuitable. First, the atomic rocket. The fireworks invented by the Chinese and their monumental descendants used for space travel have one thing in common. Like the motor of a car, they work by the internal combustion engine principle. Thrust is produced by energy liberated when the chemicals burn. They are called chemical rockets. Gases expanding and rushing through the open end of the engine provide thrust. The same principle holds true for both the liquid and solid fuel systems. The performance of chemical rockets has doubled during the past 2 decades, and their growth is now leveling off. But the source of power that will provide performance greater than today's most advanced chemical rocket engine is the nuclear rocket engine. An engine based on the fantastic energy of the atom, of nuclear fuel, essential for flights of our astronauts to Mars, Venus, and beyond. Essential for auxiliary power to operate a base on the moon. The nuclear rocket does not burn fuel in the same way that chemical rockets do. Instead, it carries the lightest of all elements, liquid hydrogen, as a propellant. The heat source is an atomic furnace, a nuclear reactor. It heats, vaporizes, and expands the propellant, and expels it from a nozzle to produce thrust. The nuclear rocket has advantages over the chemical propulsion engine for trips into deep space. The specific impulse or efficiency of a nuclear rocket can be 2 or more times greater than that of a chemical rocket. This will result in a great reduction in the weight of the propulsion system for the same payload. For some missions, millions of pounds less than chemical rockets, permitting the nuclear rocket to outdistance the chemical rocket. Today, space objectives can be accomplished by the chemical combustion rocket. But the power requirements of some future space missions will be made possible by atomic energy. The nuclear engine is versatile. It can shut off and restart as desired. And the amount of its thrust can be regulated to meet mission requirements. The heat in the nuclear reactor is produced by the action of tiny bullet-like neutrons, the electrically neutral parts of the atomic nucleus. When a neutron strikes an atomic nucleus, the nucleus may split, releasing at the same time radiation and heat. In the process, additional neutrons may hit other nuclei and build up a chain reaction that can yield tremendous amounts of usable heat out of small amounts of nuclear fuel. Uranium is the most practical fuel for this purpose. Since slow-moving neutrons are more likely to cause a chain reaction than fast-moving neutrons, moderating materials are used to slow them down. The reactor's activity is started, stopped, increased, and decreased by the use of neutron-stopping materials such as cadmium or boron. Reflector material, such as beryllium, that bounces escaping neutrons back into the active area, greatly increases activity. Now, to take advantage of the tremendous heat created by the fission process, the propellant hydrogen is forced through the hot core. As it absorbs heat, the gas expands to a veritable hydrogen hurricane, exerting thrust as it is forced out of the nozzle. Since the hydrogen expands to produce thrust and does not burn, it is not necessary to carry oxygen to support combustion. While the theoretical advantages of the nuclear rocket are impressive, the practical applications offer great challenges. The scientists and engineers of the Atomic Energy Commission and the National Aeronautics and Space Administration combined forces to meet these challenges. The name of the program, Rover. The mission, develop the hardware for tomorrow's astronauts. This is Kiwi, the first nuclear reactor in the space program during a nozzle-up ground test in Nevada. Kiwi served as the basis for an experimental NERVA engine. The NERVA reactor's power level is about 1,100 thermal megawatts. Hoover Dam, with all its powerful generators, produces about 1,250 electrical megawatts. If a giant electrical heater were connected to Hoover Dam, it would take almost the entire output of the dam to produce the same amount of heat which NERVA produces from a reactor core just slightly larger than a kitchen stove. This experimental engine system has 55,000 pounds of thrust. The next generation reactors, the Phoebus series, may approach almost 5 times as much power. These nuclear rockets will be used in space as upper stage on vehicles boosted from the Earth with chemical rockets. The men who design and build the nuclear rocket are looking ahead to the time when our nation's space vehicles will be used for extended manned lunar operations, for manned planetary exploration, and unmanned deep space probes. From the nuclear rocket, we turn now to the atomic electrical power plants. Spacecraft need electricity to satisfy the demands of the various subsystems. The need for a continuous supply of electrical power is especially great in manned space vehicles with their complex life support systems. Radio and television receivers and transmitters, telemetry devices, computers, and other scientific instruments. This power may be provided by batteries with relatively brief lifespans or solar cells, which have their limitations. For example, solar cells, because they can only be energized by the sun, cannot operate on the shadow side of the moon. Or they may be damaged when the craft passes through radiation areas, such as the Van Allen belt. Also, as spacecraft become larger, they require higher capacity power sources. At these higher power levels, atomic energy will be especially useful. Two different types of atomic power sources have already been launched to power spacecraft. The radioisotopic generator, known as the atomic battery, and the atomic power reactor, the isotopic generator. This satellite launch in 1961 made history, the first use of atomic power in space. Still operating, the satellite carries a radioisotope generator as a supplementary source of electricity for its radio transmitters. This first space generator, about the size and shape of a grapefruit, weighs about 5 pounds. Its rated output is about 2.7 watts. Radioisotopes of an element release energetic particles. When they are stopped in the surrounding material, they produce heat. Heat is converted into electricity. This is accomplished by a series of thermocouples, each of which converts heat directly into a small amount of electricity. When two dissimilar metals are joined in a closed circuit and the two junctions are kept at different temperatures, an electric current is generated. There are no moving parts. Here is a series of thermocouples as used in an isotopic generator. Ultimately, the lifetime of such a unit is limited only by the length of effectiveness of the atomic fuel. That may last years, as in the case of this isotopic unit, to operate a remote weather station. Under most circumstances, the life of an isotopic unit is much longer than the life of a chemical battery or solar cells. When space vehicles become larger, isotopic generators will become relatively less economical. The larger nuclear demands can be met by an auxiliary power reactor. The principle of creating heat is similar to the method used by the space propulsion reactor. Only in this case, the reactor and power generator are much smaller, such as this 970-pound SNAP 10A reactor power system. In this case, the heat produced by nuclear reaction is converted directly into about 500 watts of electricity by 1440 thermocouples. April 3rd, 1965. The first time a reactor was put in orbit. During its operation in orbit, the atomic reactor produced 500,000 watt-hours of electricity. An exact copy of this flight unit completed more than a year of successful, uninterrupted testing on the ground. Eventually, reactors of this type will produce much more power for the same weight. Reactor systems of the future will provide housekeeping power for observation and weather satellites, orbiting laboratories, and communication systems sending signals directly to your radios and TV sets on the ground. In other types of space auxiliary power reactors, the conversion to electrical power will be accomplished by heat exchangers, feeding a conventional turbogenerator. Astronauts of the future will travel in spacecraft propelled by nuclear rockets. The huge array of instruments and control devices in their spacecraft And in those they will leave in space, on the moon, and on other distant places in our solar system, will receive electricity from nuclear power generators. Men in space through the magic of the atom.